Hi folks, we're going to take a look at number 2 from the February 12th homework. So they give us a velocity time graph and they ask us to answer the questions given below. Okay, so again, very important to remember that this is not the position time graph, but the velocity time graph. So let's take a look at the questions. This is, when is the object moving in a positive direction? So in order to answer moving in a positive direction, you just have to see when the velocity is positive. Okay. So here's our x-axis. So looks like it's positive from about 0 to maybe 7 seconds. Okay, so here we'll put t in seconds. So we have t is in the interval 0 to 7. Okay, and then union, because we're combining that with other sets. And let's see what else we have. This looks to be about 14 to about 44, we'll say. Okay, so from 14 to 44 seconds, the velocity is positive, which means that it's moving in a positive direction. Okay, so that's all we need to determine. So this is why it's important in the notes to really take a look at what the sign of each of these functions tell us about the motion of the object. So the next one says, explain why you cannot determine when the object is moving toward and away from the point of reference. Okay, so if you take a look at the notes, you'll see that in order to determine when you're moving toward or away from the point of reference, you need information not just about the velocity, you also need to know the position function. Okay, so for example, we saw that if this is our point of reference, okay, if the position is positive and the velocity is positive, you're moving away. But if your position is negative and the velocity is positive, opposite sign, we see it's moving towards. Okay, so here the reason why we can't is because we don't have the position function. Okay, now not only do we not have the position function, there's no way to determine the exact position function from its derivative. Okay, so we should also say that we can't determine the position function from the derivative. Okay, so as we saw in a previous lesson, that the best you can do is come up with one possible function based on knowing its derivative, but you can't know the exact function. All right, so let's go to C. It says, when does the minimum velocity occur? When does the minimum speed occur? All right, so here we remember that there's a difference between speed and velocity. Speed is the absolute value of the velocity. So if I'm looking for the minimum velocity, I just have to look for the absolute minimum y value on this velocity curve, which seems to occur at 10 seconds. So we can say here, part 1 at 10 seconds, that's the minimum velocity. But the minimum speed, remember the speed is given by the absolute value of the velocity. So all these negative components get turned into positive components. So in the end, you realize, the minimum speed is just going to be 0. Okay, when the velocity is 0, the speed will be 0. So when is this thing equal to 0? Well, at 7 seconds, at 14 seconds, and at 44 seconds. Okay, so here we have at 7 seconds, 14 seconds, and 44 seconds. Okay, since the velocity is equal to 0, and so the speed is equal to 0. All right, so let's go to D now, and let's see what D is asking us for. It says, when is the object speeding up and slowing down? Okay, well, this is something that we can determine, because while we only have the velocity function, we can figure out the sign of the acceleration function. All right, so what I'm going to do is I'm going to set up, instead of working here, I'll try to change this up so that we can come up with two number lines. Okay, so I'm going to start with the number line. In fact, I'll use the one that's here. Okay, so let's come up with a number line for velocity. Okay, and we see that the velocity is positive up until 7 seconds. Okay, so till 7 seconds it's positive. and then it's negative up to 14 seconds. Okay, and then from 14 to 44, and this whole area here, it's positive, and then from 44 on, it's negative. So now what we're going to do is we're going to do the same thing with the acceleration function by looking at the slopes of the tangents of the velocity. Okay, and we see here that they're positive for the first, this looks to be maybe 2 seconds. Okay, so up until 2 seconds, the acceleration is positive, but now the slopes of the tangents of velocity, in other words, acceleration, are all negative till we get to about 10. Okay, so here they're negative. All right, and then they become positive again until what looks to be about 24. Okay, so positive here. And then if we look past 24, we see that they're actually negative all the way down to infinity. Okay, they never become positive again. So for this whole area here, it's all negative. So now what we have to do is just take a look at where the signs are the same and when they're different. So let's start with speeding up. And here we have slowing down. Okay, so for speeding up, it's when the signs are the same. So we see that from 0 to 2, they're both positive. So that'll go in the speeding up section. Okay, then we see from 2 to 7, opposite signs. All right, from 7 to 10, we see negative and negative, so the same sign. So that means that it's speeding up. Okay, here from 10 to 14, negative and positive, opposite signs, so slowing down. All right, and then from 14 to 24, we see positive and positive, so speeding up. All right, then from 24 to 44, opposite sides, so slowing down. And then lastly, from 44 on, they're both negative, and so speeding up. Okay, so this is 44, and we'll say to positive infinity. We're not quite sure exactly where it ends. All right, so again, always a nice idea to set up these two number lines one on top of the other so you can much more easily compare the signs of the function. All right. So, all right, let's take a look at E. E is saying describe the motion of the object in the long run. All right, so when you see words again like in the long run, they're essentially saying end behavior. So as time gets really, really large, what can we say here? Well, we see that the velocity seems to be approaching a constant value of -1 meters per second. So in other words, what does that mean? It means that it's approaching a speed of 1 meter per second, but always going in the negative direction. And if we think about the acceleration, what's happening? Well, we know that the slopes of the tangents are getting flatter and flatter and flatter, so the acceleration is approaching 0. All right. What we can't say anything about is what's happening with respect to the what's it called? Whether we're going toward or away from the point of reference. You know, who knows? Maybe it's so far beyond the point of reference that even for like 100, 200 seconds, it's moving in the negative direction. It may never actually reach the point of reference. So again, we can't make any determination based on the position of the function because we don't have that one there. All right, so here, in fact, F asks us about acceleration. So we'll say here for E, we'll answer the velocity. We see that the object approaches a speed of 1 meter per second, and we'll say always moving in the negative direction. Okay, and then for F, we can say that the acceleration approaches 0 in the long run. Okay, so just a couple little quick recaps. Step number 1, when you're given a function's graph, make sure you know what the graph represents. And second of all, make sure you know what information you can and can't get from this graph here. So in this case here, it's the velocity versus time. So you can get information about the rate of change of the particle. You can get information about its acceleration, but you have no information about its position. Okay, that's it for this one.